Okay, so in this section we are talking about areas and distances, and we're going to start off with an example. So here it asks, suppose you leave your house and drive east at 60 miles per hour for 2 hours. How far would you be from your house at the end of that 2 hours? So you're driving straight away from your house, and this is easy to compute since this is a pretty simple problem. So you just take how fast you were going and multiply it by how long you were driving for. So that would be 60 miles per hour times 2, and so that would be 120 miles, right? Now, what we can do is think about representing this graphically. So if I wanted to think about what the velocity function would look like, well, since it's completely constant, it would just be here at 60, it would be a horizontal line for from 0 up to 2, right? So that is what the velocity function would look like. And notice that this 120 is going to be the area underneath this velocity function. Okay, so we can actually use this idea in more complicated situations. So of course this isn't very realistic because you can't leave your house going exactly 60 miles per hour right from the get-go. So you need some time to accelerate. So Next, we'll think about what would happen if you spend the first 30 minutes of your trip accelerating. So that's not so realistic, but just to have an example that's easy to work with, what would the velocity function look like? Well, for the first 30 minutes of your trip, so that would be from here at 0 up to 30, or half an hour, you would be accelerating up to 60, and it says at a constant rate. So it would be a straight line from 0, 0 up to that would be, I guess this is 1/2, so that's 1/2 in 60, and then after that you would be driving at that rate, 60 miles per hour. Okay, so this is what your velocity function would look like. And then we can also ask how far away you would be at the end of 2 hours. And the same idea applies. So we can actually just compute the area underneath this curve, and it would give you the distance traveled. Okay, so the best way of doing this, see, I've shaded in this triangle. And then the rest of the shape is a square, or yes, it is, well, not quite a square, I guess, if you're looking at the units. So the best way to do this is just to break it into 2 pieces, and we know how to compute the area of a triangle and the area of a square or a rectangle, and so we will just use that to give us the area under the curve, which will be like before, the area under the velocity curve will give us the distance traveled. Okay, and so anyways, traveled. There we go. So let's go ahead and do that. So the first thing we'll have is the triangle. That would be 1/2. The base is also 1/2, and the height is 60. That's the area of the triangle plus the area of the rectangle, and that's going to be, this width is going to be 1.5. right? And then the height is also 60. So we can go ahead and compute this. We would get 60 divided by 4, which is 15. And then I'll actually write this as 3/2 instead of 1.5. to make this easier to simplify. So we would get 3 times dividing 60 by 2 would give us 30. And then we can just finish this off. That would be 90 plus 15, which would be 105, right? So 105 miles is how far you would be away. Okay, so we can just think about, so instead of describing this situation, we just have the graph of the velocity, and how far would we be then? So it looks like we accelerated, we stay at 60 miles per hour for 1 hour, and then we decelerate, and notice that this part of the graph is actually negative. So what does it mean when a graph, when a velocity curve is negative? In this case, in the context of this problem, it means that you're traveling back towards home. So you started off traveling away from your house. The velocity being negative means you've turned around and are going back in the other direction. So what that means when we're talking about the distance that you've traveled is that here we're going to take the area beneath this curve. That will give us the distance traveled when you're moving away from your house, that is. And then when you're traveling back towards home, this part is actually going to be taking away from your distance from your house. So it should be negative. The nice thing about when we actually go to compute the area under this curve is that it will automatically be negative if we take as our height of our triangle, this is negative 30. I'll put that on here. Yeah. It's already negative, so it's sort of built into your computation already. So just to show that, I will go ahead and do the computation. So the area under the curve is going to be 1/2. So this is the first part is computing the area of this triangle. So that is 1/2. Again, base is 1/2 and height is 60. Then our rectangle here is width 1 and has height 60. And then we have one more triangle. It has width 1 and height, we take 1/2 times the base 1 and height 60. Okay, so that is all of the area that lies above the graph. The area that lies below the graph, or below the x-axis, or I guess it's the t-axis here. The area that lies below is this small triangle that I've shaded in, and if we take the height to be negative 30 instead of switching it to be positive, which we usually do in the context of most problems, but in this case, if we leave it alone, it actually works out really nicely. So we take 1/2 times the base would be 1/2, and our height, like we said, is negative 30, and then that will give us our distance away from your house. Okay, so I will go ahead and just give you the answer for this one instead of computing it. So if you work this out, it should give you 97.5 miles, right? And so in general, so what we've seen is that the area under the curve of the velocity gives you the distance traveled. And more generally, because we know that velocity is the derivative of position, we can make a more general statement that will also be true. So the signed area, so by this I mean, actually, we'll talk about this in a second. I will just write this down. So the signed area under f prime tells you, instead of distance traveled, it's just going to be the accumulated change of f. because we don't know what quantity f is measuring, but we can just talk about how much change has accumulated over a certain interval of the function f. Okay, now by signed area, I'm referring to the idea here that this piece that was below the t-axis was negative. Right. So we think of this as having negative area, even though that's not something that we usually do. In this case, because it does work out to give us the accumulated change, this is how we're going to treat these things. So when we say signed area, that means we subtract things that are below the x-axis and we add things that are above the x-axis. And so all the time when we're talking about area beneath a curve, it's actually you travel from the curve, wherever you might be along the curve, and go down or up until you hit the axis, and then you stop. So that's why I've shaded in this area right here and nothing below it down here. And then also if you are, oh, oops, I made a mistake. This shouldn't be shaded here. It will have the same area, but this is going to be here. There we go. Right, so you go from here up to the axis. Okay.